Great. I think we have time for questions for both Leander and Bonnie. Anyone in the New York node? Leander, do you want to go? Yes, please.
Hi, yeah, very nice talks. I was curious just a little bit about void finding and void. You mentioned ellipticity, they're like void filaments and void pancakes and stuff. How do you, what are the different options for void finding and void characterization and shapes?
So you can see. So currently we're using the bit void finder. It basically uses Voronoi cell tessellation and watershed transform to find voids.
Yeah, I mean, you have a bunch of different algorithms. For example, like spherical underdensity, and they each have their pros and cons. So ideally, you would look at signal to noise maximization. But we haven't done that.
I see. And are any of the are the posteriors that you show, do they depend on those different algorithms choices?
They would probably depend a little bit, but I don't think it would be a huge dependence. I mean, basically the speed finder is very good at finding sort of weirdly shaped voids, but sometimes it also finds something it's like very funny.
Right.
Yeah, Douglas.
We have a question here in Paris.
Should I go ahead or no?
Let's do the Paris one first.
Yes. In the second talk, could you explain why you're able to constrain the scalar spectral index with the voids? What is giving the information?
Do you mean like what the void data we are using to constrain the NS?
Or like, what is the reason you're sensitive? Because, like with weak lensing, or like in two-point statistics in the late universe, we don't have that much constraints on NS, but somehow you have already good constraints.
I think because we're using the machine learning models, so we don't know exact reason behind that. But void are usually more contains more information from the early universe, so we're more confident about its constraining power on NS. If that makes sense.
Adrian, do we have any Slack questions?
Someone in New York. So I guess Eve is asking, could you contextualize the expected neutrino mass constraints from voids as compared to other statistics?
Right. So, I mean, I showed posteriors that we obtained from the galaxy autopower spectrum alone. So I guess this is only about redshift surveys. I don't know. Yes, and we also compared to what you get from EFT, and it's qualitatively similar.
Douglas, last question.
If I was doing this analysis in the traditional way, you have autocorrelation function and then some stuff to do with voids and so on. I would have to consider carefully the covariance between the different measurements because they're not independent.
Yes.
So I don't know how that works.
No, the covariance
you're
is
doing.
fully accounted for.
So you have a covariance in the.
So we consider the joint data vector of all these statistics, and then we compress it. And this is what's passed to this neural ratio estimation algorithm.
So you run a whole bunch of simulations to estimate the covariance first?
So, with these implicit likelihood methods, you don't have this traditional separation between covariance simulations and data vector simulations. You just run simulations with different random seeds at different points in your parameter space. So it learns jointly the dependence on parameters, the mean, and the covariance.
Okay, that sounds like magic. So let's talk at coffee or something. Yeah, thanks.
Let's thank both speakers again.